Welcome to lessons 7.3, 4, and 5. We're going to look at Bohr's model and the emission spectrum of the hydrogen atom. With spectrums, you can have a continuous spectrum, or you can have what we call a line spectrum. So if you were to take a spectroscope and look at the white light that comes from the sun, not looking directly at the sun, but looking at the white light that comes from the sun, you would see a continuous spectrum of red, orange, yellow, green, blue, indigo, violet. And that's indicated over at the right, although it's not in color on this particular PDF. A line spectrum will only show discrete wavelengths. And so what I would have students do is I'd have them use the spectroscope to look at the white light coming from the sun. They'd get something that looked very comparable to a rainbow. Then I'd have them take the spectroscope and look at the lights in the classroom, and they would still get a rainbow, but they would see specific lines, and it wouldn't be continuous. And then I would pull out the gas emission tubes, and they would see the different gases. If they looked at hydrogen, they'd see that hydrogen only has the 4 different lines. Now those lines have different colors to them. You can't see that on here, but if they use a spectroscope to look at hydrogen through the diffractometer, they would see that they would only see 4 distinct colors or 4 distinct energies. The significance of that line spectrum, so Niels Bohr was able to look at that line spectrum and say that only certain energy levels are allowed for the one electron that's in the hydrogen atom. And if you look down here, you'll see that the hydrogen atom can have, so the center circle represent the nucleus, the lines out represent the energy levels 1 through 4 actually there, because there's only 4 circles around that center circle, and that electron can move to those particular energy levels, but it can't stop anywhere in between. And so that's what Neil speculated. He came up with the quantum model of the hydrogen atom. The electron in the hydrogen atom moves around the nucleus only in certain allowed circular orbitals. And so Bohr's model is probably the model that you made when you were in elementary school and perhaps junior high. With Bohr's model, he came up with an equation, and his equation is listed there. Nuclear charge on a hydrogen atom is only going to be 1, so these are pretty simple problems in terms of 1 squared. The top is always 1. So when we're dealing with the hydrogen atom, as we move into bigger atoms, it's something different. N is an integer. N represents how far away from the nucleus the electron is. A negative sign implies the energy is bound to the nucleus is lower than it would be if the electron were an infinite distance. Now, electrons will have a tendency to try to stay in what we call their ground state. That's the lowest possible energy state. And so in order to either require, if energy is put in or if energy is given off, that means it's moving towards that ground state if it's given off. And if it's being applied, the electron is being moved away from that ground state. Change in energy is going to be the energy at the final state minus the energy of the initial state. And then we have another equation for the wavelength of the emitted photon. So let's go ahead and look at these equations in terms of, let's put them into practice. Practice problem number 1 says calculate the energy required to excite the hydrogen electron from level n equals 1 to level n equals 2. Also calculate the wavelength of light that must be absorbed by a hydrogen atom in its ground state to reach the excited level. So if we use the equation that Bohr came up with, energy equals, and then you have this constant, and the top one, energy at level 1, we calculate that, energy at level 2, and then we subtract those, we end up with 1.63 times 10 to the negative 18 joules. So we're going to use the equation here to calculate what the wavelength of light that must be absorbed. And so we use Planck's constant, we use the speed of light, And then we use the energy we just calculated to come up with this, and that would be basically 122 nanometers, so it wouldn't be something that we can see on the visible spectrum. Practice problem number 2, calculate the energy required to remove the electron from a hydrogen atom in its ground state. So in its ground state, it's going to be at 1. And if you remove it, that means your n is infinity. And so anytime you have infinity on the bottom, you end up with 0 there. And so in order to remove the electron from a hydrogen atom in its ground state, you running through his equation, you end up with 2.178 times 10 to the negative 18 joules, and that's a positive number. Calculate the maximum wavelength of light capable of removing an electron for a hydrogen atom from the energy state characterized by n equals 1 and n equals 2. And so we already calculated n equals 1 on the prior page. And that's, well, actually, no, we just calculated n equals 1 up above, because we got 2.178 times 10 to the negative 18th. Calculate that out. That's about 91.2 nanometers. And then if we're looking at the change from n equals 2, to remove it completely, we have to recalculate, get joules, put that in over here, and then we end up with 365 nanometers. So a different wavelength of light is going to remove an electron from energy level 1 and from energy level 2. For which of the following electrons transition into hydrogen atom does the light emitted have the longest wavelength? So when we're looking at these, notice that when we calculate wavelength, we're looking at this number down here. And in order to get that number bigger, we have to look at this part of, this part of the equation. So that's what we're doing here. So if we go from n equals 4, or n equals 4 to n equals 3, so final minus initial, we came up with this number. 4 to 2, final minus initial, we come up with this number. And then we keep on going. So we're doing this part of the equation to come up with that. Then that number is going to end up on the bottom of this equation. And so the bigger number on the bottom is going to give the smaller number on the top. So which does the light emitted have the longest wavelength? So smaller e gives you bigger wavelength. And so the smallest e is going to be the n equals 4 to n equals 3. Kind of process that one a while. If you have questions, please don't hesitate to ask. And then with Schrodinger and quantum mechanics, Schrodinger's wave equations, if you take a physical chemistry course, you'll get more of these. But just looks very, very Greek. Just wave equation shows where the electron's position is in three-dimensional space. An orbital is actually considered a specific wave function. So we talk about an s orbital or a d orbital or a p orbital or an f orbital, and those are actually, we make it sound very easy. Schrodinger actually has equations that identify each of those. Heisenberg's uncertainty principle, you cannot know both the position and the momentum of a particle at any given time. And so Heisenberg did some complex mathematics to come up with that scenario. And then in terms of when we're talking about what orbitals look like, a lot of instrumentation was done to where the electron would exist to kind of show us what the orbital looked like, and that's called a probability distribution. So those are what gave us the shapes. That concludes lesson 7.3, 4, and 5, and we'll continue with this in the next lesson.